Okay, so let's begin. Sort of continue with the last lecture by Nelly. Please.
Okay, hi, it's me again. It will probably be the last time you see me for a long time after the end of the school. So yeah, cherish the opportunity to listen to me. I'm joking. So I will also put in a timer just to keep track of things. And we're continuing on my favorite topic, of course, resource-directed quantum thermodynamics. And I will begin with a short recap of what happened on Tuesday night, just in case all of us were half asleep. I was half asleep. So anyways, so quick recap of what happened on Tuesday. We talked about thermal operations a bit more, and we highlighted two central properties, one being Gibbs preservation, and the other one being what I call covariant, which is that it commits mute with time evolution. And we saw this beautiful hierarchy of different thermal processes, which comes from either generalizing the thermal operations or considering special cases of it, which were maybe more motivated by experiments, right? And we saw that there were problems and opportunities in both directions, and that was kind of the state of the matter. We looked into thermal majorization, which was the essential technical tool when it comes to asking questions about state transitions. So if I want to ask the question of whether I can go from rho to rho prime via thermal operations, then the answer is more or less thermal majorization. In some cases, it's necessary and sufficient, but in general cases, it's just another solution. Yeah. So we looked a little bit at that, and we noted this idea of catalysis. The fact that you can tag on an initial, you can tag on an omega C state here at the very beginning, and keep it exactly at the target point as well, and uncorrelated from the system. And we show that thermal majorization itself arises to this structure where catalysis helps. And it was kind of cute. And then we asked our questions about what are the monotones that remain under catalysis. We talked about how this kind of irreversibility in thermal majorization can be systematically taken away in different limits. The first step we took was using a catalyst, and then the next step we took was considering many copies. And also we noted this curious idea of saying that even if we don't take many copies, it is sufficient maybe to allow for catalysts such that you allow for final correlations to exist between system and catalyst. And interestingly, that gets rid of a lot of the additional constraints on higher moments that we see in the generalized free energies. And that leads us back to the second law that we are wonderfully familiar with, which is the non-equilibrium standard free energy. So that was pretty much what we talked about on Tuesday. And today I have only one agenda, and only this agenda, which is to elucidate a little bit more what exactly is the role of the catalyst in a thermodynamic approach. This is just because I'm starting to miss my cat. 72 hours before I will be here again. Okay, and this is an important topic because if we think about right now, the things that we know about catalysis, it's basically something that arises from the study of majorization, the mathematical structure. We have no real intuition about why exactly is this additional system useful. We have no intuition about how are we going to construct it. We have no intuition about what exactly it is, right? And this is also, when this idea wasn't really clear what catalysis is, it was also the time where I started getting bombarded by people who say, you shouldn't use the word catalysis. You know why? Because chemists have used this word for so many years, and they mean something very specific when they talk about a catalyst. Essentially, it doesn't only come with the connotation of something that you just added on and it magically helps the reaction, but people have very specific ideas on what happens in catalysis. So the idea of saying that you have some energy barrier to a reaction, and the adding of a catalyst allows you to kind of lower this energy barrier. So it opens up dynamical pathways in the reaction process, and it kind of boosts your reaction rates. So that's maybe very roughly speaking. I'm not a chemist. What people have in mind when they first think about the idea of catalysis. Okay, and the idea that you have to return the catalyst back to its original state also is motivated by the fact that you don't explicitly consume the resource in the catalyst. And this is also why you can use it in repeated manners, right? So what I do want to argue is that the word catalyst is actually very justified, and it not only translates to what we know in thermodynamics, but because of the fact that majorization is so prevalent in the whole field of quantum information processing, what we see is that catalyst not only has a very significant meaning in terms of physical ability of in quantum thermodynamics, but it also has its general power or understanding that we can translate that into general quantum information process. So that is the conclusion that we had in a recent review paper, which was done by the three of us. I used to say that I used to like to introduce my two co-authors and myself as three different people from slightly different generations of people who have been very obsessed with the topic of catalysis. So all of us have been working on catalysis throughout our PhDs and early years of the postdoc, and that was why we kind of grouped together and had like nice topics to always discuss. So we decided to write a review on catalysis because of that. So we have like a WhatsApp group called Catalyst Fan Club to talk about catalysis all the time. And weekly we had Zoom meetings to kind of gather literature and share together with one another what have we recently learned about catalysis. And that was really fun for me. I do hope that at some point, if people get curious, they read the review. We try to write it such that we give the kind of guiding intuition behind why a catalyst works. And you will see parts of that today. Okay, so we've seen this, but I also want to talk about this very basic, not even physics-y kind of scenario of a catalyst. But it takes with it the idea of that the problem of designing a catalyst has some kind of mathematical flavor to it. Okay, and this is what is known as the problem of the Tower of Hanoi. It's something that maybe if you have kids, then your 3-year-old or 4-year-old plays with it a lot. You have this kind of rods, and you have this that you can put on those rods. And you can try to think about a game of transferring this from one rod to another. And if you are additionally given the constraint that you cannot kind of destroy a hierarchy in the sense that you cannot put a bigger disk on top of a smaller disk, then you can, so that's the rule of the game in some sense. That's a constraint in the problem of the Tower of Hanoi. So the question is, well, can you find the minimum number of moves that you would need in order to transfer this stack of desks from one rod to another? That's maybe the question. Now, minimally, you will definitely need 3 different rods, even if the task is to kind of move this just to a second rod. If you do not have this extra place to stash some of your disks temporarily, there's no way you can perform this kind of operation with respect to that constraint. But it's known that if you have an additional stack here, then you can you can move this thing, and the number of optimal moves, at least for the case of k equals 3, is known. But obviously, if you are allowed many more such empty bars, then you would maybe come up with even a process that would even do this faster, right? So what you see here is an analogy of a catalyst where this rod, which started out initially empty at the beginning, goes back to its original state, but it actually enabled the transformation under the presence of this additional restriction that we have, right? And so this is, in some sense, like a catalyst. And this transformation is the task of that state preparation that we were thinking about. And the number of moves is talking about, let's say, the complexity of an operation, etc. Right? So this is a kind of a more toy-like example of looking at an example of catalyst. Now, we come back to the problem of what exactly is the role of a catalyst in a thermodynamical process. And I want to illustrate this with a maybe small story. So we've talked about the unique position of a Gibbs state quite a lot throughout this entire winter school. We talked about the fact that it is passive. We talked about the fact that we cannot extract work from a Gibbs state. And in some sense, you can come up with many different settings of what it means to extract work and how to quantify that. Now, as long as your theory kind of makes sense and is consistent, you will always come to the conclusion that if you have a Gibbs state, you try to extract work from it, you cannot in some sense, due to the kind of passive structure. Now, we're going to look at a particular example of this, which is related to the scenario of fluctuation theorems. And this is also a scheme that we have already seen so far, because it's essentially, I have a system state that comes in as an input. I try to measure in the energy eigenbasis. I get some initial probability distribution on the energy. And after that, I put it into some channel. Let's assume that this channel is unitary for now, which means that it can be a protocol that tries to kind of decrease the amount of energy or tries to extract work from your system. And at the end, you measure again. And so work is then defined as this stochastic random variable. That is the difference between your initial and final energies. And so the average version of the second law would say that if you think about the amount of work extractable from the thermal state, there being the input here, then the amount of W on average should be smaller or equal to 0. Okay, but in fact, we can prove something more. So in fact, if we apply the Jasinski equality to this scenario, then it says that not only the expectation value of the work is smaller or equal than 0, but the expectation value of e to the power of minus e to the power of beta W is actually equals to 1. Okay, so that's the situation that we are in. And these two conditions, it's kind of easy to see that you can go from here to here. Is this obvious to people why this is the case? It's actually kind of, if people are not so familiar with this, the ideas that come behind this is always to think about e to the power of beta W being a convex function. So a convex function would be something that looks like this. And so it has the property of, if you take the function applied on some average value, then this would generally be larger than, this is going to be the average of e to the power of beta W. And here you would have e to the power of beta applied on the average amount of work expected. And so this has to be larger than this. So in information, it's just Jensen inequality. It comes for all convex functions. And so this inequality, this equality actually implies the other. But the converse is of course not true. And this contains information on higher moments that need to also be fulfilled. Okay. And so we So before we continue on this, what I wanted to also say is that there's the question of how fluctuation theorems may relate to thermal operations, because in the original setting that I have a unitary channel, which doesn't necessarily mean that you are energy preserving and all that. So it looks very different, and you have these energy measurements that are different. But in fact, you can extend this by looking at what happens if you emulate this unitary, which is generally some driving, into a case where you are making use of some additional battery system that gives rise to the work that you're inputting into the system, together with some thermal operation, which acts with the energy preserving unitary. So fluctuation theorems have also been derived in that kind of setting. So I just wanted to make the quick connection between fluctuation theorems and the framework of thermal operations. But we're back to this picture. Okay, this is a very simple fluctuation theorem. And we first note that this equality is actually not only satisfied by arbitrary unitaries, but in fact, it is satisfied by all unital channels. Okay, it doesn't need to be necessarily unitary, but as long as the maximally mixed state is preserved by this particular channel, then we are in good shape and we can apply this equality. And the proof is also quite simple. It relates to writing out the expansion of what this quantity is in terms of the probability distributions. Okay, so I'm just going to go through it quite quickly. So I have this quantity, which is summing over or averaging over the probabilities of EI and EF, which I can decompose in this form. And here I have e to the power of beta W, which is EI minus EF. So now I want to rewrite this conditional probability that we have here, but this is of course entirely dependent on the channel. So in fact, this is precisely taking the initial state to be the energy eigenstate EI, applying the channel onto this energy eigenstate, and then at the end measuring again in the energy eigenbasis and finding the probability of obtaining the state in EF, right? So that's the expression for the conditional probability. And now what we can do is we can take one of the summations and plug it in, because everything is linear. So we would have that essentially you have the summation outside here over the final energies. But whatever is happening inside here is actually the channel acting on some identity operator, right? And if this operator is preserved, so if the maximally mixed state is invariant, then E of I is also going to be just I. Then you basically collapse this inner product, and we know that these are just probabilities, so they sum up to 1. Okay, so if effectively what we have shown is that this Jarzynski equality holds for any channel that satisfies the unital condition. Now, we can ask ourselves, what about other maps? What happens when my channel deviates from unitaries or unital channels? What happens if we are talking about thermal processes in general, for example, thermal operations? Any ideas? Who said it will be different? Of course it will be different, right? But the question is why? The question is, why would, let's say, why would a process satisfy the Jarzynski equality, and why would some other processes not satisfy the Jarzynski equality? What is going on? Okay, so we could be in a case where the initial and final Hamiltonian don't coincide. Essentially, we can also be in a case where we keep the Hamiltonians and we just talk about evolving states, right? So we don't necessarily need to change the energy levels. So what is going on? Sorry? Yeah, that's something that we can see from this condition. But so the idea really is that when we talk about, so the point is that this will in general be violated. And the concept here is really that when we talk about work being the difference of the measured energy here, the reason why we assign this idea of work into this protocol is previously it was really because we are thinking of some driving protocol that doesn't change the entropy, right? And now, if you have a general thermal process that comes in here, you introduce heat, right? And so this final W that you get here from the two-point measurement process is something that captures not only the work that we're trying to do, but also the amount of heat that goes into this process. It again recalls the idea that you really need some sort of consistency when you talk about work, together with the protocol, the scenario that you are considering. It's not so obvious that you can always just take the differences in energy and get it. That's the main idea. So we can take one of the examples of a very simple thermal process, which is the process that is mapped by a quantum channel that just thermalizes everything. No matter what is the input, you thermalize. Okay, and you can make a quick example by computing what the expectation value of e to the power of beta W is. Okay, and you follow the calculations here, then actually you will get something that is the ratio between the dimension of the system together with the effective dimension of the thermostat. So this is queuing back to what Sharon was saying earlier. So the effective dimension actually pops up here for the case of the channel being a fully thermalizing map. And that is an illustration of why, in general, it's not a big deal to violate the Jaginski equality, okay? Because of heat. Now, a more important essence of what happens in the what is the constraint on work extractions, the higher moments that really come in, is that you cannot have an extraction of work that grows linearly with the number of copies of systems that you have. So that would be that would be something that is sufficient, not sufficient, but necessary condition of the Jaginski equality. And so this is a quick kind of characterization of what it means to not have extraction of macroscopic work. It is that the probability distribution, if you think about the probability distribution of extracting some work, then it has to fulfill that if it does not grow linearly with the number of particles that you put in the beginning. So this is a slightly different condition than Jaginski equality, but it's a good condition to kind of distinguish work from heat when we are talking about general channels in this two-point measurement scenario. And at this point, you're asking me, I thought you were going to talk about catalyst. Where on earth is this catalyst coming in? So right now, we are going to think about a catalyst. And let's think about what happens if my map is essentially unitary. Because what happens is that I allow a catalyst, and I say that the map is actually unitary across the system and the catalyst. And furthermore, I'm using the catalyst, I'm not really explicitly drawing anything from the catalyst, I'm just allowing it to have some correlations with the system, okay? And that's all. And so the question is whether this would fulfill Jaginski or violate it, and what does it do with the condition of macroscopic work? So it's less surprising to know that it violates the Jaginski equality. But more surprisingly, using a catalyst, what we can show is that you can bypass the condition of extracting no macroscopic work. And in this paper, what they do is they provide an explicit construction of how a catalyst when allowed to create correlations with your system originally, allows you to then bypass these stringent conditions of not being able to extract macroscopic work while still satisfying the second law on average. Okay, so that's a strange thing. So essentially what we are seeing is that catalysis seems to be able to give us this ability to bypass higher moment restrictions on your system. And it translates to tasks like work extraction and all that, just by the fact of that it is allowed to now create correlations with your system. Okay, so this is quickly summarized as these three different types of processes, one being the Javinsky equality, which unital channels would satisfy them. The other one being no macroscopic work, in general, thermal operation would fall in this category. The heat links kind of protocol that we saw yesterday would also fulfill something like this. But if we just think about catalytic unitary channels, then we can even surpass this and really get rid of a lot of the stringent conditions, while still satisfying the second law on average in terms of how much.
So can you provide some more information on, so when you say it bypasses this higher moment restriction of the Javinsky equality, does that mean like things like variance and stuff? It's bypassing those?
Variance or even higher order constraint on what your work distribution can be.
And those are things that heat would affect, or like other coherences that it's helping to in your system, or what's like intuition for why that's so okay, or why it's so.
Yeah, so the intuition, and I'm giving this actually only very briefly, is that you can actually think about the catalyst as something that stays, it stays the same locally, but it creates correlations with your system. What does that mean? It means that if you know what happens on your system, the catalyst has actually already changed. It's just preserved on average, right? So what happens is that you can think about the catalyst, which is a typical example of this, if you visualize a battery, which is a mixture of being empty and half full, and full. And this battery, if it interacts with your system, then your system with some probability extracts work out of the battery, or it kind of depletes the battery and goes gets to a state of higher demand. So it changes the state on the catalyst if you have access to the system. But on average, if you trace out the system and don't know what happens on the system, the catalyst is on average preserved. And this is in some sense if you would see that the battery in this case, if you look at the time cost-grain version of this battery, then it's essentially something that is preserved on average, which you might be tempted to call it a catalyst. But essentially, it's changing depending on what happens on your system. That information might not be readily available. So that's kind of the idea. Sound good? Okay. So we talked about, so this little story here is really to kind of express what a catalyst is useful for. And I would actually argue that a lot of things we do in thermodynamics is to kind of construct explicit protocols of catalysis. Because if we try to construct something that can be reused, meaning that you will try to run it in a cyclic way, such that it can be reused and reused, that is essentially your catalyst. So the working body of your heat engine is the catalyst when you talk about work extraction between, let's say, two bars. If you have any sort of quantum memory, which is, let's say, a daemon, you maybe need to construct the actual protocol. But the fact that you are allowed to use a daemon is precisely allowed by this framework of catalysts. And so you can also, just now the answer, the response to you was also that you can see catalyst as a coarse-grained version of a battery that is evolving in time, interacting with the system, but you're not depleting it on average. It's kind of the idea. And another idea is that you can think about what happens if you would like to kind of keep track of your thermodynamic process in a very controlled way. You need the notion of time, and you need to be able to turn on and turn off some coupling to different systems. You would use maybe a catalyst to do that, and you don't want to degrade your clock. You might want to use it for further use as well. So all of these different ways of designing systems that would work in a cyclic manner in a thermodynamical process essentially is the ability to have a catalyst. So these are the different kind of usage that you can take the catalytic framework and to kind of implement them in a thermodynamical process. So questions this far? Maybe not. Okay, so we come back to this hierarchy, and it's a wonderful hierarchy, and people have studied it in many different manners and tried to figure out the relationships between them. And now we are thinking about what happens to this hierarchy when you are given the additional ability to use a catalyst. Okay, so what do you say? What would be additional considerations of having a catalyst do to this set of different thermal processes? Who thinks it will just complicate things? Yes, you think so? Probably. So of course, there are two ways this can go, right? One way is that catalysis is really kind of perhaps making things more complicated. So in fact, like adding additional sets here to further complicate the hierarchy. But there's also the potential that catalysis actually can collapse some of the hierarchy. So for example, if you think that maybe allowing for a catalyst could potentially enlarge the set of elementary thermal operations, which were these two-level kind of operations. And maybe it's just so nice we can maybe recover a lot of thermal operations from this idea of allowing a catalyst. So there's potential for simplification when you allow for a catalyst. And indeed, what we recently did show is that in fact, okay, so there's still so in fact, what we did show is that when we consider a catalyst to be allowed, then everything that has been studied so far, which is within strict subset within the thermal operation framework, actually collapses back nicely to the thermal operations framework. And the idea is really that here the catalyst acts as this additional system, which is like a quantum memory, which models explicitly non-Markovianity, which was why those smaller subsets actually fall short of the entire set of thermal operations, because they had some inbuilt Markovianity in the way that they were set up. And it wasn't obvious at all from the beginning that this was the case. So what we show now is actually the power of having a catalyst precisely models this amount of non-Markovianity that we are injecting, and it slowly kind of bridges the hierarchy that exists within the set of thermal operations. And the key intuition here is that, well, we talked about ETOs being this two-level kind of thermal operations. And if we know that in general, two-level unitaries are universal operations. If we translate that from quantum computing, we know that. So initially, it was quite a surprise when people showed that, oh, ETOs can actually not, they're strictly a subset of TOs, and they cannot actually reach the entire set. And this mystery was there for 6 years. It kind of stalled the progress on elementary thermal operations and Markovian thermal processes, if you ask me. But what we show is that essentially you have this recovery of the gap when you allow for a catalyst. And we have this nice kind of collapse of the hierarchy. Now, it's not so clear whether going up this hierarchy, you will also recover the same thing. So this part is at this point completely unclear, whether allowing for a catalyst also kind of changes this hierarchy. So this is something that would be great, because since we do know a full characterizations of the enhanced versions of thermal operations, if we can actually bridge this gap via a catalyst, then that would be awesome. It's at least awesome for me. Okay. So with the ideas of allowing for a catalyst, there's still many questions, of course. There's the question of how do we actually decide if a process is catalytically feasible, state transitions, and how do we actually design the process and the corresponding catalyst states that allows for these things? What are properties of catalyst states that would actually make them useful? And can we find, let's say, lower and upper bounds to the required either dimensionality or let's say, the amount of resource that is contained in catalyst that is necessary for transition? So these are some of the questions that you can ask in general. And one of the good ways to see the power of catalysts comes from this basic lemma that we wrote up in the review paper, which illustrates what exactly makes catalysis useful. Okay, so the lemma goes like this. You have three systems. So you have your original system here, rho S. You have some catalyst omega C here, and you have some environment state rho E. And let's U be a unitary on the whole thing that brings your state to that brings your state into something that correlates the environment and the system while achieving what we want on the level of the system. So we are going from rho to rho prime on the system, and the unitary does that such that it achieves some effective correlation with your environment, while keeping it tensor product from the catalyst. Then, if this is true, then what we do know is that effectively you can find another operator V that does this job fully without the use of catalyst. Okay? So what this lemma is trying to tell us is when catalyst is not useful. In particular, when you have if you have a process that allows for the reaction already to happen, the transformation already to happen, with correlation only built up between system and environment at the end, then there was no need at all for the catalyst to be there. That's the statement of the lemma, which means that there are only basically three different ways as to when a catalyst could ever be used. So the first situation where it's useful is that when your catalyst is maybe not exact. If it's degraded by a little bit, maybe you can argue that that's not called catalyst anymore, but humor me for a while. So if something changes on the catalyst, of course, you don't have this exact condition anymore, and you may have help in terms of having such a catalyst. The other condition is if your final catalyst is actually correlated, there's some shared correlation with the system and the environment that is there. So in particular, the reduced state is the same, but there's some correlation. Or the third possibility is that you are in a framework of resource theories where U is free, but V isn't exactly free. So the channel that it's induced on the system is actually not permitted by your framework of resource theories. So when you have restrictions, which maybe comes from things like conservation law, because if you think about thermodynamics, strict energy conservation is the idea of what goes into free operations. So once that happens, you have certain dynamical pathways that are blocked. And so you're in the scenario of this, where you have a set of free states that are restricted. So but during these three different scenarios, you can possibly have some use for catalyst. And so this leads to different types of catalysis that are in the literature. Okay, so there's strict catalysis, which is essentially no correlations, no change, exists because you have a resource theoretic framework. Correlated catalysis, well, spells out for itself, and approximate catalysis when you have small degradations happen in the. And so those correspond to the three different factors. And of course, the picture is actually, I would say, wonderfully nuanced. There's a lot of subtlety that comes into each and every one of them. And there's also interplay between these different types of catalysis, which is why if you read the literature of catalysis, which exists all over different types of resource theories, very easy to get confused. And so what we did try to do in the review was to provide a kind of streamlining of how we should understand these different types. Essentially, the summary is that you can start off with a situation where you don't use the catalyst and you have some set of monotones. Once you go into the strict catalytic framework, then you see that additive monotones have to remain. If you further allow for correlated type of catalyst, then we saw earlier that the super additive monotones will have to remain. Okay, so that's one kind of slow systematic relaxation that we see. And we come to one of the surprises that we see in coherence theory. Okay, this relates to a surprise that was recently discovered in correlated catalysis framework for the resource theory of coherence. Now, this is obviously important for thermodynamics because thermodynamics is actually a special case of the theory of coherence because the strict energy preserving condition is a condition on not being able to increase coherence in particular. Free operations there are just the covariant type of operations that we have seen. And what do we actually know about this resource theory is the first question. But what we do know is something, it is actually on the level of what people have also studied for example, new cloning. And there's also a theory called no broadcasting theorem, which means that if you have a system here that has no coherence in some, let's say the energy eigenbasis, then what you cannot do, it's a no-go theorem that shows that what you cannot do is you cannot bring an additional system, a catalyst here, that has some amount of coherence and attempt to kind of broadcast this coherence across to the system. You can transfer it, of course. This is what Ronnie has said already before about transferring of coherence. That is possible. Broadcasting, which means that you have to preserve the coherence in the catalyst, is not possible. Okay, seems pretty much intuitive. And what recently people have relaxed this condition to say, well, maybe here we shouldn't have this strict condition of being that the system needs to be uncorrelated from the system, from the catalyst. Perhaps it will help if you allow for some correlations to have to exist between the system and the catalyst. Perhaps we can lift no broadcasting. Okay, that wasn't known actually before, but recently there was a proof that says indeed you cannot create coherence on the system. Now, what was really surprising, this was actually a result that came only in 2020, 2021, I think, is that although you cannot broadcast coherence, you can amplify it with a correlating catalyst. So the idea is that you can start out with a small amount of coherence on the system. And if you are allowed to use a catalyst that ends up correlated with your system, the coherence on the system can be amplified while keeping the local state of the system exactly the same. So in some senses, this is a funny way of not broadcasting, but amplification that is actually allowed. And there were explicit constructions on how to do this. So it was a surprise for me. And one of the implications that was very carefully studied in this Shiraishi Takagi paper was that this implies that there does not exist a super additive resource monotone for the coherence theory. And that was very special because for all the other resource theories that we know, LHC, thermodynamics, there is always a super additive quantum resource. And that is always the quantities that we know and love, like the free energy, entanglement entropy, and so on and so forth. But that doesn't exist in the resource theory of coherence, which is quite something. So then we come to a second surprise. So we come to a second surprise, which is if we think about approximate catalysis, meaning that I return your catalyst, not exactly, but I am tolerant. Maybe I want to allow for small amounts of errors. Nobody is perfect. Catalyst should not be perfect either. So what happens if we really try to make this theory not so stringent and say we do allow some amount of tolerance of error on the catalyst. Now, of course, errors accumulate, right? So if you are thinking or planning on reusing the catalyst, you don't want too large errors. So maybe on the safe side, we even think about asking for the ability to make the error really always very, very small. And the idea is maybe for each particular tolerable error you can make, you say you can find a catalyst that this is possible. Okay, so this is what we call approximate catalysis, and then you can ask, well, how should the state transitions conditions change? And you expect something reasonable, right? You expect that probably it will mean that the state transition conditions change by a little bit. That is a function of epsilon, maybe, and that's all unsurprising. Now, what happens is then something that comes out, which is coined as embezzlement in the whole catalytic theory, is that what happens if you say I can allow for arbitrarily small error, but I don't further put any restrictions on it. In particular, I allow for the use of very large catalysts, let's say infinite dimensional, etc. And what happens, interestingly, was that you realize you run into problems. And this was first studied in the case of entanglement theory, where you allowed for this additional ancilla that Alice and Bob would hold. And you would say that I would like my catalyst to be returned with some fidelity. And embezzling says that actually it's possible to construct a family of catalysts with increasing dimension, such that for any epsilon, you can actually find a catalyst of a particular dimension that allows you to kind of transform any 2-qubit state that is shared between Alice and Bob. So in particular, Alice and Bob can start from just a 0-0 state. And by using this embezzling state, they are allowed to create maximally entangled states. So this leads to basically all monotones going away. If you only require that your catalyst is returned in some small error. And this is maybe surprising in the beginning, but after you think a little bit more about it, what you will realize is that one should not think about the epsilon error here that we had quantified. For example, using fidelity or trace this trace distance. These are quantities that we know and we think are really good measures of how well you can distinguish two states. And so we treat them as very appropriate errors, right? But you neglect the fact that your systems can grow in dimension and you have extensive quantities. And resources are often extensive quantities. So in particular, if you have two density matrices, which are epsilon apart in terms of trace distance, the entropy can still grow with log n. And so that's extra change in resource, if you don't further restrict the dimensionality of the catalyst, allows for basically embezzling or stealing of resources from your catalyst and putting it in the system without people noticing. That's kind of That wasn't initially expected, but once you realize it was clear. And then the way forward would be then to make sure that when you design protocols that are cyclic, that make use of this kind of additional ancilla, you have to make sure that it's not just enough to say that you are approximately close to some cyclic process. That's not enough, because you can still be in the position where you're stealing resources and claiming maybe some advantages, whereas what you're doing is just embezzling funds. Yeah, so that is a faculty that needs to be taken care of when we're dealing with approximate versions of catalysis. And these things can be usually, so there is kind of another visualization that is kind of cute, which is that you can have one bar of chocolate and you can cut it in certain geometrical kind of ways and rearrange the pieces such that at the end you get this one cube out, and you seem to kind of restore the entire chocolate, right? But what is actually happening here is that you have embezzled this small teeny strip along this line. It's just that it's not so noticeable. And this is kind of a very nice visualization of what a catalyst is doing in that scenario. So the ways there have been many works on the idea of how do you study approximate versions of catalysis without really running into cheating problems that are in embezzling. So these are just two examples of works that have tried to address this problem. Okay. Questions so far? Yes.
I wanted to ask what you meant by amplification and not your catalyst in the system, but could you elaborate more?
Yeah, so back here, right? So what I'm saying is that, let's say here we have a qubit, so 0 and 1. So we could start off with something that is just a small superposition, that's like, I don't know, square root of 0.90 plus square root of 0.11. So there's a small amount of coherence. And if you think about processes which don't increase coherence, then obviously you cannot go to, for example, 1 over square root to 0 plus 1, right? But in fact, you can go there if you allow for a catalyst, and if you furthermore allow the catalyst to be correlated with your system.
But the state in the catalyst is intact while it's amplifying this state.
What do you mean by intact?
So the state, so I'm assuming the catalyst hasn't, like, whatever state of the catalyst is in, it has entanglement within it as well, or coherence within it as well.
Yeah.
And that is still intact while it's amplifying this other state.
Yes. Yes. So initially they started off without any correlations, and at the end here you have correlations which can be classical or quantum. But essentially, although the catalyst doesn't change at all in this process, locally it's still the same reduced state. What you see is an increase of coherence on the system. Thank you. And of course, the operations that act on system and catalyst are still covariant operations, meaning that they don't explicitly inject more coherence into the process. So it's really just a result of correlations that exist here, which allows for the system to appear like more coherent. Okay. Okay. So we talked about amplification of coherence, which is surprise 1, and embezzling, which is surprise 2. Actually, surprise 2 is older than surprise 1, but that's a fact that you don't need to know. Where does this bring us? Okay, this brings us to only one small thing that I want to mention, which is the problem of, well, now I kind of know what monotones, how do the monotones behave in different types of scenarios. Great. How do I come about to identify a suitable catalyst or determine the actual transformation? Because that's what we are interested in, right? At least in the thermodynamics community, I do want to explicitly design some protocols that will achieve a certain goal, etc. And so I'm interested in the question of design. And you raise a fair point. In general, this is not an easy problem to do. And there are a couple of useful techniques that we have developed over the many years of being obsessed with the subject of catalysis. I will share with you two of them, and you can read some of the details later if you are interested. One recipe that we do have comes when we have three operations, or we are in a resource theory, which allows for controlling freely on classical randomness. What does that mean? It means that you can always tack on some additional state and conditioning on some measurements on this additional Ancillae state, you can perform different free operations on the system. So this is set up in a very generic way. It's, in some sense, it's talking about convexity of your resource theory. So if you have a resource theory that has this type of convexity, for pre, then we know that what happens is that if we do know the possibility of going from one state to another in the many copy situation, if we do know this, then we have a recipe to construct the catalyst such that a single copy of rho can go to a single copy of sigma via this catalyst. And this is a strict catalyst, okay? So that's one recipe that we know that bridges the multi-copy scenario with the single shot scenario. No further comments on what this explicit construction is. You'll have to read to figure it out. And the only catch here is that the catalyst dimension here is going to be very large just by design, though it doesn't, I mean, practically speaking, it might not necessarily be that you need this large catalyst, but this construction in particular is a large one. Now, a more useful technique of finding a catalyst relates to a tool that a numerical tool that finite information theorists are very fond about. They're as fond of it as, let's say, the relative factor. Okay, maybe not quite, but you get the idea. So the idea is that once you have, although it's maybe not generally easy to find the entire protocol of catalysis, once you do fix an input state on the system, and once you kind of decided on the Hilbert space of your catalyst, together with the channel that you're going to implement on the system and catalyst, then it's easy to find the catalyst. Okay, so it's, if you want to optimize over everything, difficult. If you say, I kind of want to pick my operations already, so I pick my channel and I pick my initial system, then finding the catalyst is easy. And this relates to basically the fact that you can think of this description of input system and the channel as an effective channel that describes what happens on the catalyst. And once you have a map like this on the catalyst Hilbert space, on the catalyst set of states, then finding a transformation that allows for correlating catalysts is finding a fixed point of the map. The same thing. And so this always exists due to some argument on compactness of the set of quantum channels. And this is basically a convex program, which you can put it into MATLAB, and that's all. And assume that it's easily executed. So SDP methods are very common now, and people talk about the question of studying correlated catalysis. When you are thinking about uncorrelated catalysis, it gets a bit more tricky, but that is something that is a bit out of our range. So with the two sharings of different methods of catalysts, this is in some sense a summary of what we have been obsessed about over 10 years. So I hope you liked it. I hope you appreciate it. And the idea is really that today I just wanted to say that catalysis is really a way to kind of systematically include additional resources without consuming the asymmetry that is in them when you're talking about thermodynamic processes. And so it models a lot of different things like your memory, your daemon, your working body, etc. And to think about explicit protocols of this, are exactly thinking about explicit implementations of using the catalyst. And it has applications not only in thermodynamics, But a lot of these things that we discovered in quantum thermodynamics is now being slowly brought back to the field of quantum information. Which is a cool thing for me. And my friend is here to say hi again. Otherwise, I'm ending here and thanks for your attention.
Questions?
Do you have a minimal instance for some experiment to
That would have been my question.
simulation? Yes.
Yes.
And how close to-
So I can tell for qubits, different measurements,
Mhm.
and then states where it will. We have a minimal instance case. Or what is the, did you think about what is the minimal size requirement if you think it's been 1.5 systems?
Yeah, so wonderful question. Because that was initially also the idea of using small catalysts, very explicit catalysts, like just thinking about 1 qubit or 2 qubit was one of the first projects that I gave to my PhD student. So we have a work recently that really tries to explore how ETOs, which were these 2-level operations, the gap between that set of operations can be slowly enlarged towards the set of thermal operations by using a qubit catalyst. So I'm just using 1 qubit as my catalyst. And we basically found what regions or how much we can actually do that. So this is maybe a good starting point for thinking about implementations, I would say.
Because from your chocolate example, it appeared that you need a lot of catalysis
Yes.
qubits in order to make it work, or is that a misconception?
So the chocolate example is kind of small.
Yeah, you need a big chocolate in order to make it not visible that there is this little
Yeah.
thing missing, so that was my.
So if you really want to have an extremely small, almost undetectable error on the catalyst, then you really need the large dimensions, and that is something to definitely. But embezzling has always been something that whenever I give a talk on catalysis, embezzling is always the thing that fascinates people and the thing that people ask, can we do an experiment on this? To that, I would say I would love to see an experiment on embezzling. But then maybe one has to sort out a bit on the details of what type of catalyst, large dimension is natural to see in the lab, for example.
I have a list for you, which answers your question. A Stirling engine, in practice, ideally, you don't need a catalyst for a Stirling engine, it's reversible. But when you look at construction of Stirling engine, they have a catalyst. They have an additional, say, heat source that you put in heat, put back, which allows them to operate. So Stirling engine, you could say, by construction, has a catalyst built into it. And I just saw Baker now of Holodetsky, which also does something like that.
So how closely related or perhaps different are these catalysts from these Ancillae
Mhm.
techniques that people have used, using Ancillae qubits to
Mhm.
effectively work?
Not so different.
They're
Not so different. So in fact, like in the review, what we did was also there's a small section on reversible computation. And essentially what the techniques of using an Ancillae, doing so that you can do a computation reversibility is essentially a technique about catalysis. So I would say that catalyst is basically the most generic and abstract way of studying what are the limits of using ancillas without explicitly consuming them. That's all there is to it, I would say.
Is an example.
Yeah, it is. Yeah. Okay.
Other questions? Okay.
I think there was also, so yesterday I was talking to one of the participants, Tanmoy, and he was showing me actually a protocol of an auto engine, where you have 2 qubits from 2 bars, and you have a protocol that tries to extract ergotropy first. And he studies it by using basically, I think it was a 3-qubit system, right? So you have 2 qubits as your original working body without catalyst. And what happens when you add a third one? So it's a 3-qubit protocol. And what I think you show was that you can, given more catalytic qubits, you can interpolate between the amount of efficiency that you can get in a heat engine from auto to Carnot, something like that. So there's an explicit protocol. It will be good to maybe talk about it. Good. Very good.
This is a very natural point to join me in thanking Nelly.